Hello, my name is Lily Toon, and today I'll be explaining collision theory. For a chemical reaction to occur, reactant particles must collide with sufficient energy and correct orientation. This is what collision theory is. There are three main components that I have highlighted in my definition. First, the reactant particles must collide in order for a reaction to ever take place. Then, they must have the sufficient energy for the reaction to take place and the correct orientation. So, if reactants meet all of these components, they will yield products. So, the first main component of collision theory is collision. I like to think of the molecules as pool balls. So, you hit a pool ball, it collides with another one, they bounce off. This is what the particles do. This collision is what allows it to occur. They have to interact with one another in order for a reaction to happen. The second step of collision theory is sufficient energy. This can be defined as surpassing the activation energy needed for a reaction to occur. So, the activation energy is the minimum amount of energy required for a reaction to occur. I like to think of it as if you're going to go run a race, but you have no sleep, you have no fuel, you have no energy, you can't run your race because you're not prepared, you don't have the amount of energy you need to do great. It's similar to collision theory. If you don't surpass the activation energy needed to go from your reactants to your products, your reaction can't occur. So that's why meeting the minimum amount, surpassing that activation energy, is very important in collision theory and making sure your reaction takes place. Activation energy can be represented by E sub A, which will come in handy later. The third component in collision theory is proper orientation. This one can be kind of confusing for me, so I have two examples, one where no reaction occurs and one where a reaction does occur due to orientation. So in this hypothetical situation, I have three dark molecules, and then I have one dark molecule and one light molecule. If both collide, which is the first step, and they meet the activation energy, which is the second step, but they aren't oriented correctly, no reaction will occur. They will just bounce right off of each other. However, with proper orientation, a reaction occurs. So we'll show that again. Our molecules collide, which is step one. They surpass the activation energy, which is step two, and they're oriented correctly, so the reaction does occur. These are the three main concepts of collision theory, explaining why a reaction takes place. Collision theory can be directly related to the Arrhenius equation, which is used to solve for K, the rate constant, E sub A, activation energy, or temperature. So, this is the Arrhenius equation. K represents the rate constant of a reaction, A is the frequency factor, which is usually given, E sub A is the activation energy, R is the universal gas constant, which is 8.314. T is the temperature at which the reaction takes place, and E is another constant, 2.718. So in this example, it says, calculate the rate constant K for the reaction at 350 Kelvin, given the frequency factor is 1.5 times 10 to the 11th, and the activation energy is 60 kilojoules per mole. So before you ever even start, you have to make sure you're converting your kilojoules to joules. So 60 kilojoules per mole would be equivalent to 60,000 joules per mole. And then you plug in all your values into your Arrhenius equation and solve for, in this case, the rate constant K. So I converted my kilojoules to joules, and then I simplified the exponent. So you have your activation energy, which was given to us. We have R, our gas constant, and we have our 350 Kelvin. So then I simplified the exponent, and I have 1.5 times 10 to the 11th times e, which was 2.718, our constant, and it's most likely in your calculator, raised to the negative 20.619 power. So then you just simplify everything and multiply it, and your answer should be around 165 inverse seconds. So that's how you use the Arrhenius equation, which is related to collision theory. Another key component in collision theory is understanding what affects reaction rates, energy, and collision frequency. Temperature, pressure, and concentration are all key components in affecting reaction rates, energy, and collision frequency. So, how does temperature affect these things? Well, increasing your temperature will increase both collision frequency and energy. This is due to the molecules entering an excited state, which gives them higher energy and causes quicker and more frequent reactions. A great example is placing a glow stick in hot water versus cold water and seeing how it affects it. So the hot water glow stick is going to be much brighter and more vibrant than the cold water glow stick. This is due to the fact that the molecules are excited, they're moving around, they're causing many more collisions, and it's just a quicker reaction rate. And so therefore higher temperature leads to higher collision frequency and higher energy. Pressure. Increasing pressure increases collision frequency. This is due to the fact that the molecules have less room to move around, which causes more frequent collisions due to the close proximity. I like to think of it as if you have a lot of people in a big open space, they're going to have a lot of room to move around. They're not going to bump into each other because they can go around. They don't have to interact. However, if you cram all of those people into a small elevator, they're going to be bumping into each other. They're going to be, oh, I'm so sorry. Oh, excuse me. They're going to be interacting with each other a lot more because of this close proximity. Concentration is similar to pressure, but it's important to note the key differences. Increasing concentration still increases collision frequency. However, it's because the molecules are filling up the space rather than making the space fit the molecules, if that makes sense. So I think of it as if you have two people in an elevator, they're going to stand on opposite sides. They're not going to interact much. They're not going to bump into each other. They're probably not going to say anything because they don't have to. However, if you fill up that same elevator with a lot more people, they're going to, again, bump into each other. They're going to say, excuse me. They're going to be interacting a lot more, which leads to more collisions. Another factor in collision theory that affects the minimum activation energy needed for a reaction to occur is the presence of a catalyst. I think of this as a train going around a mountain versus a train going through a mountain. So a catalyst provides an alternative pathway that lowers the minimum activation energy needed for a reaction to occur. So rather than the activation energy being high way up here, a catalyst lowers it so that the reaction can occur at a lower activation energy rather than high one. So a catalyst doesn't necessarily cause more reactions, but it makes a greater percentage of collisions successful. And it does not affect the total energy, only the pathway taken. So it only affects the threshold it has to cross in order for the reaction to occur by lowering the activation energy. So, to sum up collision theory, for a chemical reaction to occur, reactant particles must collide with sufficient energy and correct orientation. Activation energy, E sub A, is the minimum amount of energy required for a reaction to proceed. Collision theory can be related to the Arrhenius equation, which can be manipulated to solve for K, activation energy, A or T. And temperature, concentration, and the presence of a catalyst all have an effect in different ways according to collision theory, such as collision frequency, reaction rate, energy, and activation energy. And that is the end of my video. Thank you for listening to it, and I really hope you were able to learn something about collision theory and that my video was concise, and thank you so much.